Now we are starting on chapter 6, which covers word problems for integrals. Now you might think, what word problems are there? The area under the curve, right? We're calculating the area under the curve. That's the meaning of the integral. Well, you are exactly right. The first thing we're going to do is calculate area under the curve. Except that in chapter section 6.1, we're going to do the area under two curves. In other words, you have your area isn't just your average area under the curve, but it's defined by two curves. That is, there's the top curve, which marks the top boundary, and then the bottom, there's another curve on the bottom that marks the bottom boundary. And the area we want isn't just the area under the curve, but the area in between those things. And how would you do that? And if you were to look at this, you might say, how? Well, it seems like the obvious way is simply to calculate the area under the curve on top, integrate that, and subtract it by the area under the bottom, right? And then you should be good, right? Now, if that's what you think, you're absolutely right, and that's what we're gonna do in this section. So let's look at example 6.1, which is on page 625, where we're supposed to calculate some area between two graphs, similar to what we just saw. You have a function on top and the function on the bottom is supposed to find the area in between. Now notice the theorem 6.1, where it gives you the area of, it just gives you the area of figure out which function's on top and which one's on the bottom, so that you subtract and don't end up with a negative area. Otherwise, you are getting exactly the right idea. So what we do is, now in this case we have a two fairly simple function in which you have an area, and then so you just subtract the two function and then integrate it. Okay, very straightforward. So please do example 6.1 as your homework, and let's move on to example 6.2. Example 6.2 is not particularly different from 6.1. The only thing is, the problem doesn't really tell you where to integrate. They just want to know what is the area in between these two things. See, you have two graphs. The one on top is the parabola, the one on bottom is straight line, and then the question is, what is the shaded area that is their intersection? But it doesn't tell you where the endpoints are, so you have to. So there's extra groundwork figure out where the graphs intersect. Okay, and which you can find out very fast if you graph it on the Desmos graphics calculator. And once you figure that out, then integrate from those endpoints, and you should do just fine. Okay, so that's example 6.2. Please do that as your homework as well. And then the next one, example 6.3. Now what do you have? Now you have two graphs, okay? And they want you to the problem with these two graphs is that they have the intersections intertwined. That is, the graph that's on top, f of x, at times gets to the bottom. So if you simply blindly integrate from one end to the next, the two areas will subtract each other, because part of it end up being a negative area. So what you have to do is figure out where it all goes. That is, where the intersection happens, and then calculate the integration in two parts, and make sure you keep the positive value for each area, because your goal is to figure out what the total area is, and you don't care if they're positive or negative. Okay, you don't want the negative area to subtract out your positive area. So please do example 6.3 as your homework, and we'll move on to example 6.4. Yet another different situation where you have two graphs, okay, and even a third line that says, well, we want to figure out where the shaded area is. But the shaded area has two top lines. The first part goes from 0 to 1, that's for x squared. And the second part goes from 1 to 2. Yeah, that's 2 minus x. So you just calculate you slice the area into two chunks, and then calculate each one. So please do example 6.4. And then one one last variation, okay, is what if your area is not under the curve as in under x, but it's under y. In other words, you have to tilt your head, okay, like uh, like this or like this, whatever, and look at it sideways. Well, how would you do that? Well, tilting your head and integrating sideways makes no difference whatsoever. Okay, you do the exact same formula, except that now instead of integrating with respect to x, you integrate with respect to y, and you integrate from the small to the big and take whatever's on top, which when you're sideways, on top sideways, subtract the function that's on the bottom sideways, and then come up with the right answer. And as an example for that, the next example is example 6.5. Where's example 6.5? Okay, example 6.5 wants you to redo example 6.4 by integrating sideways. Now, the benefit of integrating this thing sideways is that then you don't have to have two functions. So much. You only do one function. Although you end up doing the exact same work though, so it doesn't really. There's no real benefit here, I don't think, because you still have to find out where the intersection is and then integrate sideways. It's still a good practice, and sometimes certain functions might have a distinct benefit whether you integrate along x or integrate along y. But anyway, so that's the last example. Please do that one as well. Example 6.5. And having said all that, we have come to the homework section. For homework, which is on page 633, please do problems 1, 2, 3, 4. Sorry, I read the examples wrong. It's page 633, problems 5, 11, 15, 25, 29, and 35. And then with that, we finished the first section, which is relatively easy. Things get a bit harder from this point on. But for the first section, we enjoy an easy time and do a few problems of homework. And when you come back, I will go over some of the homework. Now that you are done with your homework, let's look at some of them. Number 15. Which there are 3 lines, and we are trying to figure out the area that's bounded by all 3. So the first line is y equal to 12 minus x. The second line is square root of x. The square root of x is something like that. Is the inverse function of y equal to x squared. The y equal to 12 minus x is a negative line going down, has negative slope, so it slopes down this way. So we'll draw it something like that, okay? And then the third line is just y equal to 1, which is a horizontal line. Y stays at 1 for any x. So now we have 3 lines. Let's label our lines. This is y equal to 12 minus x, y equals to square root of x, and finally this is y equal to 1. Alright, so then the best way to do this is probably we'll integrate along the y value, and for that to happen, we have to figure out what is the intersection, at least the y value for the intersection, because we're integrating from 1, because y equal to 1, but what is that? Okay, figure out what that is, then we're good. So to figure that out, we'll solve for x out of these 2 equations. That will become, the first equation becomes x equal to 12 minus y. The second equation becomes x equal to y squared. And when you set these 2 equations together, 12 minus y equal to y squared, which means y squared plus y minus 12 equal to 0. So then you do the good old trick from algebra, where it gives you that is y and y, and the difference is only plus 1, so plus 4 minus 3, which multiplies into 12. However, we obviously need a y value that's positive, so we will reject that one, so we'll choose y equal to 3. That should be a right answer. And then with that, we know where to integrate. So we'll integrate this thing by, we'll do our integration okay, which is the top line is y equal to 12 minus x. Sorry, we have to reset it. The top line becomes 12 minus y. So we have 12 minus y, and then subtracted by the bottom line, which is x equals to y squared. We have to represent everything by y because we're integrating along the y-axis. And then we have to integrate from 1 to 3, and then we have a dy right here. All right, so now that is a fairly straightforward power rule integration, although it comes from 3 parts. So at this point, I just plugged it into the definite integral calculator. I include one in the homework description. So anyway, but the book also has one too. You can use whichever one you find, and then I end up getting 34 over 3, I guess. Okay, which is the right answer according to the back of the book. So that marks the end of number 15. The main part is you do have to find where the intersection is, which is a little bit of grunt work. But overall, it does works out very nicely. Well, this is more grunt work here, but we're going to skip it by using the good old calculator. Okay. Actually, I should mention that when I was doing this problem, I didn't even do this part. I just graphed this thing in a decimal calculator who was able to identify that y equals to 3 right here, so I skipped this part. So, but you can do either one. You can calculate it yourself, or just have the graphics calculator do for you. There's nothing wrong with using the graphics calculator as long as you know how to do this. So there's no reason to do it the millionth time when you already know it. But so that's for most of the homework, is acceptable to me if you simply find those intersections by the graphics calculator. Next, let's look at problem 29, where we have 2 graphs that both represented by x equal to some kind of y value, which means you should integrate along the y-axis because that'll work out much better. In fact, I don't even think it's possible to do the other way, because extracting y out of here is not going to be simple, okay? And let's just not skip that hard work. So the first thing we want to do is you want to type this equation into the Desmos graphics calculator. That one turns out to work like a dream. Okay, you don't even have to change x to y or anything. The calculator is so smart that you just type in exactly as is, x equal to y cubed, etc., and type in the next equation, and then it shows you this particular graph that looks something like what's the graph? The graph looks like this. I will draw a copy here. Let's see. Okay, we have one graph that goes, I think, to 1. Okay, so one graph goes down to 1, something like that. That's the parabola. And the other graph is the y cubed that goes down like this. And then goes down this way. So what are we trying to do here? We're trying to integrate this area, okay? A very narrow, odd-looking area, but nevertheless we can still integrate. And then this point is 0, x equal to 0. No, sorry, x equal to 1. That point is 1, 0. X equal to 1, y equal to 0. And this point, the other integration point is x equal to 8, negative 8, y equal to minus 3. Okay, now, so we're going to integrate from the smaller number to the bigger number. Okay, so here's our integration, which means, and then we're going to take the function that's on top, now we're going to lean our head sideways and look at it, which one's on top. If you lean your head sideways, and then on the positive side, okay, and then well, anyway, the point is then then we on top would be the top function would be the cubic function, where y3 plus 2y squared plus 1, that's your top function, and subtracted by the bottom function, which is minus y squared plus 1, and then dy. Now at this point is where I messed up at first, and I couldn't get the right answer. What are the limits? What I put in is minus 8 to 1, okay, because I wasn't thinking. Well, we're actually integrating from the y-axis, okay? So you have to remember to integrate from minus 3 to 0. Otherwise, you're going to get garbage. So after I did that, and then everything looks weird, so I did the right thing, okay? After I messed up at first, I did the right thing and integrate from minus 3 to 1, and then I plug all the stuff into the calculator. I'll clean this up a little bit maybe. But that's, yeah, so it becomes 3y squared, okay, plus that. But in any case, by the time I plugged it into the definite integral calculator, I got 27 over 4, which is the right answer. Now, if for some reason you don't have the access to any such calculator, then you just do it the hard way, which is not that much worse. I mean, it's just it's just a power rule. So yeah, but it'll take maybe a minute or two longer, which I'm more than happy to save. Okay, I don't like to waste my minutes. And then so that's problem 29. Let me erase the board. Next, let's look at problem 35. Now in problem 35, we have two graphs, which I plotted on the graphics calculator, and it looks something like this. The x equal to 2y looks like, well, whatever. It's just a line, okay, which goes from here to there through the origin, whereas x equal to y plus y cubed is a cubic function, but it also goes through the origin like this. And the region we want to calculate is whatever is in here, right? Two parts, okay, all this stuff. Which means that you have to do this carefully, because if you simply subtract and integrate from, I don't know, here to here or whatever, the graph, see, what used to be on top might be considered the bottom later, and then you will come up with the area being 0 because they got canceled out. You see, because one of the area will be negative. So the way to get around that is you simply integrate from halfway and then double the area, and that's what we're going to do. And I lost my page. Give me a second here. And being that the stuff is all in terms of y, x in terms of y, that's a big old hint that let's integrate in terms of y. So to do the integration, first we figure out where the end point is. What is that? That is minus 1 minus 2. Yeah, I mean minus 2 minus 1. Minus 1, and then the one on top is then 2 comma 1. All right, so integrating from with respect to the y-axis, make sure that we do it from minus 1 to 1, or in our case, being that this is an odd function, these are odd functions, well, it looks odd to me, but anyway, so we're going to integrate from 0 to 1, okay? So that's what we're going to do. So we're only going to calculate this area, the positive, easy one, and then we'll double it. So we'll write down the 2 right here so we don't forget to double it. And then the integration of the y value goes from 0 to 1. And then we'll do the subtraction. What's on top? On top is the straight line, which is 2y. And then on the bottom, if you tilt your head, this way towards the positive x, you tilt your head this way, then what's on the bottom is the cubic function, or y plus y cubed. And then there's dy, and that should be the right answer. And then you can clean it up slightly. It becomes y minus y cubed. And then you plug it into your beautiful little calculator, and the calculator spits out the answer 1/2, which is the right answer at the end of the book. And with that, we finish this particular section.